you're all going to type in the parent function, which is the one I've highlighted in red. That's the number one graph you're going to need today. It's going to stay on your screen literally all day. And then you're going to pick this graph that is associated with your desk number to type in. I'll give you a second to do that. This is on Desmos, by the way. .com/practice, yeah. If you're sitting in group number or desk number 1, you graphed this one. What did you guys say happened to compare your function to this one? What words did you use?
Yes.
Yes. The parent function started at the origin. What happened to this one? Which way did it move?
Yes.
I don't know.
Left, maybe right.
It moved to the right. Cool. People who are number 2, where did yours move?
Down.
Up.
Yeah.
Person who number 3, where did yours move? It shouldn't have moved up.
It should not have moved up. Yours moved to the left.
Which way did it move, y'all? To the left. And then the last group?
Down.
It moved down. What can we notice about these equations and how they differ and how they're the same? Tell me some stuff. What's up?
The ones that move to the left and right are parentheses and raised to the power of 2.
Cool. Did y'all hear what he said?
No.
He said the ones that move to the right and left, because y'all told me this one moved to the right, this one moved up, this one moved to the left, and this one moved down. So the ones that moved right and left, their numbers are on the inside some parentheses, and then the squareds on the outside. What do you notice about the ones that moved up or down? There are no parentheses. It's like I took the parent function, I just tacked on a plus or a minus at the end, right? Those are some things I need you to notice. Did you also notice that when you added something to the very end, it went up because positive numbers are up, and when you subtracted something, it went down because positive numbers are down?
Yeah.
What do you notice about the left and right, though?
Positive goes to the left and negative goes to the right.
Yeah, and on a number line, doesn't normally the left mean negative numbers and the right mean positive numbers? So what can we make a conclusion about these?
They're opposites.
They're opposites. Those are things we're going to need to know today to do our notes. Now, one thing I do want you to do is always today, when I say clear your Desmos, I don't mean clear out your parent function. This one right here should stay in your graph literally all day. It's your parent function. It's the OG. It's the original function. It's the OG, original gangster, original graph. You know, see what I mean? OG. See what I did there? Haha, that's funny. No? Okay. Yeah, give me the pity laughs. That's fine. This is the Now I'm starting to feel like you're just actually laughing at me, not with me. This is the parent function. This is the one that started all parabolas. Every other parabola is made from the parent function and doing what we call transformations to them. I'm going to teach you all about the transformations in the next couple days. We're only doing 2 types of the 3 transformations we can do, but there are 6 types in those 2. It's like a weird, whatever, umbrella term. But what I want you to do is in your Desmos, always keep f of x equal x squared there, but I want you to make it dashed and black, because that's how I'm going to show you the parent function forever, is that it's a dashed graph as if it was there and now it's not, like it disappeared. But that way we can always compare our new graphs to that parent function. I'll show you what I mean. All right, there are 6 vocabulary words we're learning today. They're the directions that this graph can move, as well as its reflections. So on your notes, your transformations notes, LOL. See what I did there?
I just got a picture of Optimus Prime.
Yeah, Optimus Prime is here to teach us about transformations.
He's the evil. He tried to kill Bumblebee.
Yeah, but he still is a transformer. On this page, I have your parent function for you. Take your highlighter right now.
Because
Take your highlighter, and I want you to highlight this box that says parent function. Because if you forget what the parent function is, it's there for you right now. The parent function is f of x equals x squared. It's that most boring version of a parabola we can have. Every answer is 0, basically.
It's the best kind of
And it's a positive parabola. So there are 2 types of translations. Highlight the word translations. Translations is my movements. It's how I'm going to move the graph, specifically how I'm going to move each coordinate point. The easiest coordinate point to look at when we're doing translations is the vertex.
Didn't we do this in 8th grade?
You did do this in 8th grade. What you did is in 8th grade, you took pictures of like triangles or quadrilaterals on a coordinate plane, and you moved it around, doing sort of transformations actually.
I never did.
To each coordinate point. So you might have said every coordinate point, it moves down 9, so you took every y coordinate, you subtracted 9 from it. Or if it moves side to side, you subtracted that from the x coordinate. That's the same idea that we're doing here. The same words are going to be used because we will do dilations, making it bigger or smaller, but not till next time. And we will do translations, which is moving it around, and we will do reflections, which is just like the mirror image thing from 8th grade. So this should look familiar. You've just never done this with a parabola. You've done it with shapes like a triangle, which honestly I think are harder. So like you've already done the hard part. Now let's get to parabolas. Okay, there are two types of movements, two types of translations. We have our vertical translations, and we have our horizontal translations. We did already notice that the vertical translations are going to be added and subtracted on the outside of the function, and that the horizontal translations are going to be on the inside of the function. Let's talk about them one by one, okay? If we look at the vertical translations, we have two options to either go up or down. We've already kind of noticed this, but let's talk about it again. What do you notice about the up transformations?
Positive.
Positive. So when I want to go up, I'm going to add a positive number to the end of my parent function, and it should take every point bloop, and slide it up. If I want to go down, what am I going to be doing to each point in my parent function?
Negative.
Subtracting numbers from it. So that all of those points bloop, move down. Did the shape of the parabola change at all?
No.
No, just literally taking this positive parabola and either moving it up or moving it down. That's all a vertical translation does. Now let's talk about the horizontal ones. If I want to move to the left, what did I have to do on the inside?
Add it.
Add it, which is kind of the opposite of what makes sense, because normally going to the left is where negative numbers are. So there is an acronym we're going to use in this class to help you remember that, and it's called HIO. H-I-O. It stands for horizontal transformations are inside the function and go the opposite way than you think. Horizontal, inside parentheses, opposite directions. Horizontal, inside, opposite. Tell your partner what HIO stands for.
Horizontal. It's a parentheses. Opposite.
Horizontal is inside the parentheses and is opposite. Okay, so that means if I want to move to the right, since right is normally positive, what sort of numbers am I going to see inside? Negative, the opposite. Very good. Okay, those are your shifts, our movements around the graph. How we go up or down is just adding and subtracting numbers either on the inside or on the outside of parentheses. Cool, right?
Yes.
The other type of transformation that we're going to talk about today is called our reflections. Do y'all remember reflections from last year? Yeah, what did reflections do?
You're flipping them.
We're flipping them. So we're going to be flipping the graph. This is how we make sad parabolas. Okay?
Or happy one.
Or happy ones. They always start happy though, because if you remember the parent function is a positive parabola, so it's a happy parabola. And if we do what? What do we do to make a sad parabola? What is this saying right here?
You give it a negative.
Give it a negative in the very front. Makes it a sad parabola. Now this is called a reflection over the x-axis. You do have to tell me which axis it's flipping over, and here's why. Highlight the x-axis for me on this first one. Isn't my parabola flipping over that axis? Like I'm taking my positive parabola, and if you know, look at this is the x-axis, I'm just going to go bloop, flip over.
Yes.
That's called a reflection over the x-axis. We can also reflect over the y-axis. Where is the negative when I'm reflecting over the y-axis?
In front of the parentheses.
Is it inside or outside the parentheses?
Inside.
Inside the parentheses, which means it's part of my HIO group, so it's going to be inside and opposite. So instead of flipping over the normal way that we think, it's going to flip over the opposite. It's going to flip over the y-axis. Highlight your y-axis. That's a reflection across the y-axis. How does this one look?
It doesn't.
It doesn't. It literally looks the same. Because check it out. If I'm back to being a positive parabola,
And you just
this was the x-axis, so that means this is the y-axis. I'm going to flip it over the y-axis. Did anything change?
No.
No, my arms look exactly the same in the same spots that they were before. For even functions, which is what this is called, reflections over the y-axis don't really make any sense because they land right on top of each other. Let me put this down for a second. In odd functions, which we don't do in this class. You're going to do them next year. This is what an odd function might look like. Okay, this was even,
Oh, the weird.
symmetrical. This is called a cubic function. It's odd. You don't have to know this at all, but I just want to show you something. If I were to do a reflection over the y-axis and flip over again, does this shape look like this shape? No, so not all the time will it be no visual change. Just for quadratics, though, we kind of ignore this transformation because it doesn't look any different. But there are times when this transformation does look different. We're just not going to talk about it in this class. Yeah? It is part of the things you need to know, but it's not a huge emphasis. Any questions about this flowchart?
9.
No. All right, we're going to show you how to do these transformations to different functions. Are you ready? Yes. What's up? All right, we're moving on. So we're going to go to the inside of this packet. We're going to spend some time doing each transformation one by one. What have I given you on the inside of these notes? What is that?
You gave our base marker.
Ooh, what is it? It's not the base function. What's it called? Parent function. Parent function. It is the OG function. OG. Okay, it's a parent function. It is really boring, so I know why you said the boring function, but this is called the parent function. Now, I've already told you what this is called, but based on... That's not a highlighter. This equation right here, where am I adding numbers? Am I adding it on the inside or on the outside?
Outside.
The outside. So that means it's going to be a vertical translation.
Going up.
And how many units am I going to shift this up?
1.
Which means that every point moves up 1 unit. I'm okay with you drawing arrows for the direction. Everything else we're going to write out today, but the arrows for up, down, left, right, you can draw. So we think that because this says g of x is the parent function plus 1, that every single point on that parent function will just move up 1. Let's make sure we're right. So we think that this one right here, this vertex, how many is it going to move up?
1.
Bloop, so I should plot another point literally 1 step above it, okay?
Yes.
And then this one right here is going to move up
1.
1,
And the other one also 1.
up 1,
And the other one.
up 1, up 1. See how I've taken every single coordinate that I gave you on the parent function, specific, and most especially the vertex, and I'm going to move it up 1 unit. Well, now I can play connect the dots. And I've written the baby parabola from the parent function by just shifting it up 1 unit. As a vertical translation up 1 unit. But don't take my word for it. The thing I highlighted in black, all of that, I want you to type into your Desmos. Don't get rid of your parent function in there. I want you to see and make sure that we are right. Type all this in to make sure that this transformation actually did what you've graphed. You should not have to ever ask me if you got it right anymore, because you have a tool to be able to show you visually that this transformation occurred.
We are correct.
Let's let everybody type it in. You're a fast typer compared to everybody else. So if you want to highlight it or you want to circle it, this is what we're typing in. G of x equal to f of x plus 1, which says the new function named g takes the old function named f and adds 1 to it. Did it move up 1? Did we graph it right? Way to go, us. Every single point moved up 1 unit. Cool. Let's do the next one. What's going to happen in this next one?
It's gonna go down.
How do we know it's going to move down?
Because it's a negative.
Because there's a negative at the end. It's not inside. And how many is it going to move down every time? 4. So every point is going to move down 4 units. So we can sketch this before we go to Desmos and make sure we know it's going to happen. We're going to take each coordinate, and I'm going to take this vertex. How many am I going to draw below it? 1, 2, 3, 4 units below it. That's where I draw my coordinate. Each and every point I count down 4 and draw my coordinate. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Once I've got them on there, I can play connect the dots and graph it. Oh man, please draw better parabolas than me.
How is this?
pretty good. Make sure there's arrows at the end though.
Oh.
These graphs keep going. I know my parent function here doesn't have arrows at the end. It's because the graphing software I use doesn't use arrows at the end, but when you can draw it, you can write them. So please give me arrows. And then don't take my word for it. Go ahead and graph the black highlighted function on here and make sure that it did actually take your parent function and move it down 4 units. G of x equals f of x minus 4. The new function says take the old function and move it down 4 units. Check it in your Desmos. Yeah, move down. So visually, we can tell this happened.
Yes.
Easiest thing to do is check it visually, but we can also start to see from the equation what's going to happen. That's the goal.
I want the homework.
Now the next one. What's going to happen here?
We're gonna move it to the left.
To the
But it's
Okay,
inside.
that way, that way.
Yeah, it's inside the function, which means we're going to think hi-o.
No, yeah, it is the left. Oh, my bad. I was looking at the wrong one.
Hi-o reminds me that if that thing is horizontal, it's inside parentheses, and it goes the opposite direction than where I think it should.
It's going to the right.
So I'm going to move to the right how many points?
3.
So every coordinate or every point moves to the right, the opposite of negative, 3 units. Because it's going the opposite direction since it's inside. Horizontal is inside, goes the opposite way. So let's count our points. We know that this is the vertex, is where we start. So to graph this, we're just going to move it 3 to the right. 1, 2, 3. That's the left, Miss Quigley. You're right. So we're going to move it to the right. 1, 2, 3. It's going to end up here.
Oh, I just graphed it the wrong way.
Yeah, I totally wrote a left arrow. That's so embarrassing. This goes to the right, please. Huh, my bad. I know my lefts and my rights, I think. Every single point, though, gets to move 3 units to the right.
I don't want to draw.
And once you got to move 3 units to the right, you can graph your parabola, play connect the dots. And you have a nice looking parabola there that is shifted or translated to the right 3 units. But again, don't take my word for it. You can always check your work and my work in Desmos to make sure I didn't make a human error.
Yeah, I trust.
Too trusting. I wrote the wrong arrow for left and right. You got to check me on things, y'all.
Well, I mean, I already did it.
Check it on Desmos. Make sure it goes the right way. Did I do it right?
yes.
Sweet. Should never at this point, again, ask me if you did it right. You can check your work.
Oh yeah.
Now, typo on this one. On the next one, you see how there's a big G right there? Oops, that should be a small lowercase g, so change it real fast. But on this one, on the g of x equal f of x plus 4, the plus 4 is inside the parentheses. So what is this one going to be? Is it horizontal or vertical? Horizontal, because hi-o reminds me horizontals are inside parentheses and go the opposite direction. So normally plus is to the right. So this time it's going to show me it's going to the left. The opposite. So every point, I know, moves actually to the left this time. And how many is this one going to move to the left?
4.
How do you guys know it's going to be 4 units?
Positive 4.
Because like literally the number 4 is there. That's how we know how many. Because the number 4 is there. So we take all the points, especially the vertex, and we're going to move it 4 units to the left. 1, 2, 3, 4, and that's where I draw the point. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3.
Homework is going to be easy again.
Mm-hmm. But again, don't take my word for it. You can always check me.
Check.
Please. I keep writing arrows the wrong direction, so you want to make sure you got it right. Paul, check it, please.
Is this all we're doing for notes? Okay, then I know. You want some baby cereal? I didn't play it. Who is this? Ooh. Yeah.
All right, we're going to move on to the reflections. Because up, down, left, right, that makes sense. Insides is the left and right. Outsides is the ups and downs. But when we go to the reflections, we have two types. Oops, didn't get rid of those. We have two types of reflections. The first is called a reflection over the x-axis. So again, with your highlighter, I would like for you to highlight the x-axis just so we know what we're flipping over. I also want you to highlight the equation and put a big old arrow where the negative sign is. So put a big old arrow as to where that negative sign is. Is that on the inside or on the outside?
Outside.
Outside. So is this one going to be the weird opposite one? No, it's going to be the happy to sad parabola. So every point in a reflection, yes, flips over the axis. But the way that that happens to flip over the axis is that we count how many jumps it takes me to get from the current point in the parent function to the x-axis, and then count that many away. What? You're right. Here's the first point right here. If I had to jump down to the green x-axis, how many times do I have to jump to get there? One jump. So when I plot my next point, how many times am I going to jump below it? One. If I jumped once, I only jump once. If I'm here, how many jumps does it take me to get to the x-axis?
4.
So to plot the next one, how many do I go underneath?
4.
1, 2, 3, 4. This is where my next point would be. That's how we start reflecting these points. This one jumps down 1. So to get away from it, I jump down 1. This last point that I'm going to plot jumps down 1, 2, 3, 4. So underneath it, I go 1, 2, 3, 4. Now, if I have my vertex, how many jumps does it take for the vertex to get to the x-axis? It's already there. So do I have to jump anywhere?
No.
No. So it actually gets to stay exactly where it is because it's on the x-axis. And there's my reflected sad parabola. A negative parabola. That's when the minus sign or the negative sign is in the very front. Makes it a sad parabola. Sad parabola.
I literally went ahead.
But on the next one, since some of y'all are getting ahead of me, we're going to do the same thing. This time, where is the negative sign?
It's right.
It's inside the parentheses, right? Oh my goodness, I have been clicking the wrong things. Okay. It's inside the parentheses, which is a high O. That means it's the opposite from normal, which means nothing's going to happen. But let me prove that to you. It's going to flip over the y-axis. So highlight your y-axis. And we're going to start flipping these with the same idea when we flipped the x-axis. Flips over y-axis. If I'm this point right here, how many jumps does it take me to get to the y-axis?
None. Wait, 1.
One jump. So to get away from the y-axis, I jump 1 time. Okay, kind of on top of it. But if I was that original point over here, to get to the y-axis, how many times did I have to jump?
1.
So how many times do I jump away? Look at what's happening. Literally every point just jumps onto its other partner. If I'm here, how many times do I jump to get to the y-axis?
2.
So away I go 2. And again, you're going to have these kind of like end up right on top of each other. How many does it take for the vertex to get to the y-axis?
None.
It's already there. So it gets to stay there. So when we graph this, it should end up right on top of each other, which is no visual change, but technically it's still reflecting over the y-axis. It's flipping over the y-axis.
We just gave it arrows.
But don't trust me. I want you to check both of the reflections and make sure they do exactly as I said. Okay? Put in the parent function and then put in both of the reflections, maybe not at the same time, to see it flip over the x-axis, become a sad parabola, and then flip over the y-axis, which means literally nothing changes. Your turn. Go for it. The first part says to sketch each transformation, then describe the transformation of f of x equal x squared. That's the parent function that is represented by g. Now, again, that means you need your parent function the whole time. I highly recommend that when you go home and it doesn't show up as a dashed black line, that you at least make it dashed so that that's the way you're learning. Okay? So if we were to put the parent function into Desmos, and then also put number 1 into Desmos, we need to see what's going to happen. Some of you might be able to tell me from the equation what's going to happen, but some of us might still need the graph. So go ahead and take a second and type in both the parent function and then the equation from number 1 into Desmos. Based on the Desmos graphs that you guys just graphed, we would do the following. We would say that this is a vertical...
Translation. Do we have to write how many times it went down?
Yes, so you say vertical translation. You can use an arrow for the direction, but I do need 3 units because that's how much it moves down. Vertical translation down 3 units. It did also ask me to sketch it, so don't forget about that part. I know I didn't give you pretty points here. You can find them, I'm sure, but if you want to make sure at least your vertex moved down 1, 2, 3, and then give me a good estimate for the other ones, which some of you will figure out how to do a good estimate nonetheless. You sketch that parabola, and you have graphed and finished entirely number 1. I don't just want the transformation, I do want the graph. Remember, graphs end in arrows and have a very accurate vertex, if nothing else. Do y'all see how I want 1 through 9 answered? Cool.
What about number 10?
We're going to talk about number 10. Once you get number 9 written down, go ahead and flip it to number 10. So I can talk about number 10. I'm going to give some people more time to catch up. I think I see... almost. So on number 10, it's going to ask you again to compare... Oh, we're going the wrong way. Describe the transformations of the graph of the quadratic parent function. Graph each on Desmos to compare the parent function if needed. Because I'm not asking you to graph here, but I am giving you a hint. You see these 2 bullets? How many transformations do you think are going to be in this answer? 2. You see down here where there's 3, how many do you think there's going to be there? So if you don't answer 2 or 3 of them, you haven't finished the question. But if we look at number 10, compared to the parent function, we need to figure out what's happening. We turn to handy dandy Desmos to graph it for me so I can visually tell you what those vocabulary words are. Let me show you. So what we would write, since we noticed via Desmos that this graph flipped over and scooted up, is that this is a
Reflection and vertical translation.
reflection over the x-axis and a vertical translation. What direction?
Up 7.
Up 7 units.
Oh, we actually.
I want the whole thing. The only thing you can shorten for me today is the direction. You can give me an arrow for up, down, left, right. But I want everything else written out. Does that make sense on how I want these answered?
Yes.
So holding on to your vocabulary is going to be really important. Those 6 words you're going to use over and over again, and making sure you tell me what's happening to this graph. A lot of it is easier to see visually than with the equations, but some of you might be able to do this without actually graphing anything. Totally possible. But I highly recommend graphing them. Now, we've got like almost 9 minutes before we leave. So do a couple more before you start packing up, just to make sure you know what's going on before you leave here. If you have any questions, flag one of us down. We're here to answer your questions. Yay, Transformers!